Welcome to AI for Good, the leading action-oriented, global and inclusive United Nations platform on AI. Organized by ITU, in partnership with 40 UN sister organizations, and co-convened with Switzerland. The goal of AI for Good is to identify practical applications of AI to advance the United Nations Sustainable Development Goals and scale those solutions for global impact. In today's session, we're counting on you to use the live video wall feature to ask questions and post comments to help create an engaging discussion. We encourage you to stay until the end to chat, connect, ask questions, and network with our distinguished panelists and world-class AI experts in the neural network. It is now time to kick off the session and welcome our first speaker. The floor is yours.
Hello, everyone. Good afternoon or morning, and welcome to today's session in our AI for Earth and Sustainability Science Discovery series. I'm Maria Piles from Universitat de Valencia, and I'm co-convening the series with my colleagues Gustavo Camps-Weiss, Markus Reinstein, and Joachim Denzler. This seminar series is an initiative of the ELIS network, that's a European network of excellence in AI, to foster the AI in Europe. And we come with the support of ITU and the AI for Good program. I like to take this opportunity to thank you all for deciding to attend the talk today. And just to mention that this is the 11th talk of our series, and this will be the last one. And then we plan to start the seminar series again after the summer break. And this the AI for Good Global Summit will be also having a workshop on the role of AI in tackling climate change and its impacts. So for today, it is our great pleasure to have Maaike Zonneveld joining us. She's an associate research scholar at Princeton University and also an affiliate assistant professor at the University of Washington. And fresh news is that she will be moving to her lab to the University of California, Davis next month, and looking for new members, possibly. So a little bit of info. Maaike has pioneer methods for physics-informed models in the ocean and climate, automated regime identification, and machine learning applications which are trustworthy. So the core motivation of her work is to deliver actionable information to decision makers, both in the physical and the biological ocean. She has contributed to national and international policies, fundamental scientific discovery, and also climate model development. Her work has been highlighted in No Artificial Intelligence Strategy and also has informed the basis of New Zealand marine protected area legislation. So that's how close her research is to actionable applications. She has given over 60 invited talks. It will be number 61. Has been featured on major podcasts and review articles in the field of machine learning applications in oceanography. So thank you very much, Maaike, for joining us today, and over to you.
Thank you, Professor Piles. I will share my screen. All right, here we go. So, like Professor Piles said, I'll be joining UC Davis soon. But today, what I'm about to tell you might be unexpected, but it's actually true. And that is that the next most important revolution in AI and AI applications is not going to be having large language models like ChatGPT search the internet for us. No, it's going to be having neural networks and other tools from this toolbox really be able to address and solve some of the fundamental problems facing humanity from threats, for example, from climate change. And the work that I'll be showing you today, I hope, is going to convince you that we really need fundamental rethinking and fundamental interdisciplinary thinking to start addressing some of these challenges. And of course, the future under climate change is going to be harsh, and we know that we need new tools. We're seeing these crises emerge, and here my work, like Professor Pila has mentioned, has impacted national and international policy, as well as helped develop these models that we need, together with having broad impact. And overall, this talk is going to be about the ocean and the ocean's role in climate. And I think the ocean is one of those actors that might not be entirely appreciated in just how much it does for us. So the ocean, just as an example, has taken up over 90% of the heat that we've anthropogenically added to the system. And we really need to know what it does and how it might be changing in the future. I also want to highlight that data science and computational sciences in general have a strong and proud history with fluid dynamics and ocean and climate modeling, in the sense that one of the first big computers, this ENIAC computer, you can see John von Neumann standing in front of it, was first used for weather prediction, as well as, of course, chaos theory being originated in a similar setting. And to learn more about this and to learn more about how in a general sense you can think about this, I invite you to go look at some of the review articles that I've authored there on the bottom. And I know that the audience here is spread, and I'll be trying to cater to this also to make sure that people who might not be super familiar with machine learning concepts can gain something from this. So I'm going to be talking about two different types of machine learning here, unsupervised and supervised, where unsupervised learning is one that takes data that isn't labeled. So on the top left, you can see these dots, and we have two axes, for example, temperature and how salty the ocean is, salinity. And what we're trying to do is distinguish and find different areas within this. So you can see on the top right, we have this green stippled line, as well as the colored areas that the machine learning model, so this is what I'm calling model here, is found. However, with supervised learning, the bottom left, you can see the dots now have color, so blue and red. And what this model is now is this distinction between, okay, if I have a new dot, is this red or is this blue? And the supervised flavor here are things like neural networks, which are often referred to as a black box. Excuse me. But returning to the ocean now, the ocean is a beautiful emergent structure of circulation patterns. So here you can see the circulation in these colored arrows. Red is warm and blue is cold, and you can see that towards the southern area of the ocean, you have the ocean around Antarctica, and here we have these incredibly strong currents just sort of zooming around. And you can see that some of these warm arrows are being brought up there. That's a very important part of the circulation. In the North Atlantic, however, another region that we'll be thinking about, you can see that the circulation is sandwiched by the continents, and you have warm waters being brought up and then being brought down because they're made dense and cold or heavy, and they sink. But of course, this is a cartoon. And even if we look at figures like this is from a high resolution model, the ECHO model, and again, the colors represent temperature, and you're just seeing the surface currents. And here we can see that we have these emergent structures where things are a lot more complicated. But something that's motivated my research is to try to understand, how do these patterns emerge? What actually drives the circulation and lets us realize this very, very important but very complex system. Together with this, of course, and why now is such a great time to pull in methods, for example, machine learning or other ways of thinking about things, also from advanced statistics and applied mathematics, is that we're having access to incredible amounts of data. And here I'm showing you data from observational sources. So for example, Argo floats, these autonomous robots that are floating around in the water. And really, we have so much more technology and so much more data that not using it is something that I'm certainly really hoping to avoid. But of course, we also have data from other sources, for example, remote sensing, but also from models. And in this talk, I'll be talking mainly about models. And numerical models of the ocean generate vast amount of data. And I think it's fair to say that in terms of understanding the equations that govern this, and also in terms of understanding the models, really a paradigm lock has prevented progress, where what an ocean model does is it solves what's called the primitive equations. And these are the Navier-Stokes equation and the equation of state, so how heavy the water is. And they're very beautiful, but also very messy second order nonlinear PDEs. And I'm showing you a version there to the right, just to highlight how many parameters there are, how complicated this is. And the way we normally think about this is that we linearize or we brute force simulate. But the problem there, especially for linearization, is that the non-linearities are missing. So how do the different terms actually interact to allow the circulation to emerge? So a new frontier here that I'm very proud of being part of is to use advanced computing to try and make progress here in a non-traditional way. So in terms of climate models, now what you see here on the figure to the right is just a schematic of how a climate model might look. And what I want you to notice is that we've partitioned the entire system up into little boxes. So these are called grid boxes. And here we're going to be looking at the ocean now. So on the left, you can see a schematic of what this might look like. And within each of these little boxes, we now solve these primitive equations. And this means that because we have both latitude and longitude and depth, that we end up with a very large number of grid boxes. And for each grid box, to understand just the momentum of the ocean, I end up with over 39 different fields. And this is a lot of data if you're going from a climate model resolution that's usually fairly low to a high resolution model, which the field is pushing for. But this matters. So just thinking about this in terms of how we discretize and how having finer resolution is important, this is really important because when we can't see everything, so imagine my face, if you partition me into 5 different pixels, you won't see that I'm wearing glasses or have freckles. But if we just can't afford having such high resolution, which means that we need to make choices and we need to incorporate what you can't see into the models. So this, because this is very hard, generates what's called model uncertainty, and this is a big problem. On the figure here to the bottom, you can see these blue areas show you what the component of model uncertainty by having to make these choices induces in an empirical analysis of what's called the CMIT models. And I'll be getting back to what the CMIT models are, but they're a large ensemble of models. So this is really one of those key problems that we need to address to be able to have better simulations. So jumping into the talk here, I'll be talking about 3 different things, looking first at the Southern Ocean, this ocean around Antarctica, and looking at key processes making fundamental progress. Then we're going to be looking at how we can infer subsurface circulation. And finally, I want to end on something that I think is very important, namely how we can ensure safe and transparent methods. But jumping in here to the Southern Ocean, I first want to just pause and invite you to imagine that you're sitting in a room listening to a 200-strong orchestra playing a piece that you know and love. And here now, this is an emergent phenomenon, of course, of all these different players. And if you're trying to pick out just the 4th piccolo, that might might be somewhere that you know. This is really hard. And picking out these small components that allow the overall structure to emerge is something that's even more important in a global climate setting and in an ocean setting, because the overwhelming complexity in the system really stymies progress. So the grand challenge that I'm addressing here is finding patterns in the complex data that we have for causal understanding. And what does this mean? How do I think about this? And for this, it's worth returning to really the basis of how we make scientific progress, and this is through testable hypotheses. So if you look at the figure of the cannonball there to the right, you can see that initially it goes up and then it goes down. So if you were approaching this in a traditional sense, you would say, haha, okay, I have evidence, it goes up first and it goes down afterwards. But the approach here kind of, because of the way we use these methods, is subjective and ad hoc because you're relying on the knowledge that you have before and what you can observe. And here, machine learning can leverage the vast amount of humanly intractable data and do this in an objective sense, which I'll be showing you. And for this talk, I've highlighted the novelties here that I pioneered with little light bulbs, because I know and hope that the audience here is going to be highly interdisciplinary. So I want to make sure that everyone is able to follow. So within an equation space, within which we're working in, if we're using a model, we can define what's called regimes. And regimes is something that I define as a parsimonious combination of equation terms, where, for example, we know that in some areas we can ignore certain parts of the equation, we can cross them out, that's what we do traditionally. But now we're going to be doing this with machine learning. So just to show you what's normally done on the right, you can see just how different models are compared. Normally we just sort of draw a boundary choosing some sort of property, but here we're going to be doing something much more sophisticated. And I'll be using a model called the Estimating the Circulation and Climate of the Ocean, or ECHO. It's fairly low resolution, but it's unique and very exciting because it actually takes data and fits itself to the data in a root mean square sense. So while this is a simulation, it's been made fairly close to data. So what do we do now? I take this model, this ECHO model, and take all the data from the ocean, but actually perform a symbolic transform to bring this really high resolution, 39 different fields for each depth level, into just a 5-dimensional framework. So for each latitude and longitude, I go into my oceanographic toolbox and make this transform to what's called the barotropic vorticity equation. And the barotropic vorticity equation has 5 different terms. And within this, I'm not throwing away anything in this ocean data. And I'm able to represent everything that's going on. So the first term here is the advective component, or the component to do with being on a spinning sphere. Then we have the bottom pressure torque to do with interacting with the bottom. The wind and bottom stress, so the wind pushing against the top. The nonlinear torques, very important, and also the lateral viscous dissipation, so the ocean rubbing against itself. And on the bottom, you can see all these terms. And traditionally, like I mentioned, what you would do is to draw a circle around something that seems important, and then just see how the different terms balance. And on the bottom, you can see that for each latitude and longitude, we now have a 5-dimensional vector within which to look. And the thing here is that we're looking for patterns. We're looking for patterns in this 5-dimensional space. And this is an ideal clustering problem. This is a data mining problem. So that's what we're going to do. And here, initially, what I applied was an unsupervised model called K-means, where you can see what's called information criteria there on the left top. And here it's worth noting that the standard method fails. The machine learning model that I end up with initially is too complex. So while these traditional information criteria are saying this is a great model, actually it doesn't work, because, for example, if I want the 40th cluster here, then that's going to move around and fail some of the criteria that are important to me as an oceanographer. So what I went on to do was to build new validation steps and be able to consolidate the different terms using new geoscientific criteria. So effectively, what we're doing now is using physics-informed learning theory, and I invite you to go look at the bottom publication there for more detail. But so what does this look like? And this five-dimensional term that describes everything we need to know about what sets the ocean in motion, we discover 6 different dynamical regimes that govern the world ocean. You can see them there to the left, the different colors. And in the different colors here means that we have a unique combination of these drivers of the ocean circulation. And I want to draw your attention to the pink one here, where we have a balance between the wind and bottom stress and the planetary vorticity advection, and also this gray one, where we have a very intense version of this, but also one that interacts with the bathymetry, so interacts with the bottom. And what I want to highlight here is that some of these are known. Some of them are canonical balances that are very well known in oceanography, for example, this pink one. But now we can draw these distinct boundaries, and these are ones that are called wind gyres, and you might be familiar with the garbage patch, for example. But some of them are also completely new. And this is one of those ways that we can really create breakthroughs by now going back and looking at what's actually going on here. And this is this work around the Southern Ocean is one that was just published in Nature Communications, Earth and Environment. So what we can do is to go from this somewhat coarse way of looking at this to a new method here. And this was highlighted very prominently in the NOAA AI strategy, like Professor Pilas mentioned earlier. So jumping in now to the Southern Ocean case study, on the left, on the right, I've drawn this representation of the overturning circulation of the ocean, or the large-scale pattern circulation, again, but focused on Antarctica. And I want you to notice again that in the North Atlantic, we're sandwiched between these continents, and around Antarctica, there is no such thing. So the ocean just sort of moves around in a circle, but there are some areas where this very important action of bringing deep waters up to the surface where they can release their heat, for example, to things like the ice, is happening. And these are very important for a number of different processes. And traditionally, what we look at and what we observe and measure are confined to certain regions. So here the Ross and Weddell Seas outlined in yellow. And this is something that's really rooted in the framework of what we can observe. So the North Atlantic, for example, has similar dynamics. So a lot of the time we base our understanding on what we know and what we can see. But if we look at this now, using these dynamical regimes, these areas that we found in this equation space, we can see that actually there's nothing special about these two regions. Actually, what we're seeing is that there's a structure that actually almost encircles the entire continent. So what's going on? And what I also want to highlight is that while we don't have continents here, we actually have very rough bathymetry, or the sea floor is very rough with underwater mountain ranges. So this is also something that's really worth keeping in mind. And what we can do now is go back into these terms. And here I'm highlighting the top column row, the wind stress curl, and then on the bottom, the nonlinear dissipation. And the nonlinear dissipation is important because this is what creates a lot of the circulation in the North Atlantic. So if we now look at just the pink areas, this wind gyre area, we can see that the Southern Ocean regime, this gray regime, really very nicely picks out these very intense areas if you compare the pink and the gray, but there's not a lot of nonlinearities going on. But now if we look at this light blue area, we can see that this is where these nonlinearities really kick in and are really, really intense. And this is something that we can then use to reevaluate the circulation. So now just to highlight this and the role of bathymetry, or these undersea mountain ranges, I'm borrowing a mountain range from the north of India, just putting it in here. And imagine that this is in the Southern Ocean. What we have now is dramatic topography, and this Antarctic circumpolar current, this very strong currents and circulation encircling the continent, comes here, hits this, is deflected. And what happens here is that we have nonlinear dissipation, and this allows some of the current to cross this mountain range when it goes across it, and then initiate a gyre circulation on the other side of it. So this is really what we're seeing, and what we can really get at by taking this, taking these dynamical regimes and reevaluating some of the theory that we have. So we've introduced what we call the supergyre, a supergyre that really encircles the continent here in the yellow areas. And this is something that we say that we're observing because we can predict certain things, and that is that we have leaky subgyres that exist, together with also saying that really the thing you need to pay attention to is where these topographic features end, and that this can also guide us to where this upwelling happens that was normally more focused, or where research has more focused on certain areas. And actually, if we go back and evaluate some of the observations that we have, and remember, this is one of the most inhospitable regions on Earth. Getting these observations is really, really hard. But if we go back and reinterpret these, we can find a lot of support for this completely new way of thinking about the circulation. So the implications here is that we have a quasi-circumpolar, zonally asymmetric supergyre that actually modulates world climate, and that we can reevaluate some of the theory that was created, but to some extent rooted in knowledge that was gained in a different area, or simplified in such a way that it might be missing these important features. And we've done this by reevaluating the terms that we might even be able to observe and thus guide new strategies. And I also want to highlight that this was based on a very simple neural network model, but that a new methodology or a workflow for this is available online from my group called the Native Emergent Manifold Interrogation Method, or NEMI, that I invite you to go look at and play with and apply. So jumping in now to the second part of my talk, inferring subsurface circulation, what I want you to do is remember initially the saying that you shouldn't judge a book by its cover. And that is very true, both in terms of literature, you never know what's in there, but also for the ocean. And the ocean really is a great way of is a great great candidate for this, because we have so much data from the surface. For example, satellite observations, we can see the surface. But the problem with the ocean is that to see something that's subsurface in an observational sense, you actually physically have to go there, either with ships or robots. And even from a modeling context, sharing data that's available becomes much harder because these data sets are just so big. And the grand challenge here that I'm addressing is developing smart monitoring for climate and weather. So I mentioned the CMIP data earlier in my introduction, and this is called CMIP stands for the Climate Model Intercomparison Project, now in its 6th phase. And this is a wonderful data set. It's standardized, it's global, and they run different emission scenarios to understand what might happen in the future or what might have happened in the past. And it's great because climate modeling centers from around the world contribute to this. On the bottom left, I'm showing you some of the centers that contribute in these pink dots. And even though this is great and there's a lot of data, over 20 petabytes are shared, but actually this is still sparse from my perspective. And this is because while all the data is available when the model is run, it's actually too big to even store all the data, but certainly to share it. So using bulk metrics is very common. And when I say a bulk metric, that means, for example, looking at and seeing the strength of this very important overturning circulation, for example, in the North Atlantic, using just one number. And on the right there, you can see such an example where the MOC, the meridional overturning circulation in the Atlantic, where warm waters are brought up and then made dense to sink and return, how strong this is can be measured with just one number. And this is what you're seeing here, where the different colored dots are the different climate models. And we can see that in a scenario where we've abruptly hit the Earth with a 4 times CO2 hammer, so we're really going up, and then looking at what happens after about 140 years, we see that it's gone down. This MOC circulation, this overturning circulation, has decreased, but knowing why is very hard from this one number. So this then becomes a sparse data problem for people like me, because I want to understand the dynamics. I want to understand why, to be able to make better predictions and really understand the framework within which these circulation changes are happening. So we want to fill in this missing data, and this is something that we can do rooted in these dynamical regime frameworks. So for a climate model, the full data is unavailable. So what we do now is we use the sparse data. We use what's available, what's commonly shared in the CMIP framework. And this is something that I can do because I have this rooting in geophysical fluid dynamics, oceanography. And I'm able to select the fields that are available in the sense that I know from the initial analysis, this dynamical regime analysis, what the important terms are. So knowing what the ocean, what I have to reconstruct is very useful, because I can now create a massive labeled data set, which I need for creating a neural network. So this is what I'm now able to do, create a neural network to be able to access the climate data. And I'll be coming back to the architecture later. And this method is called Tracking Global Heating with Ocean Regimes, or THOR, which I developed together with my collaborator, Radwan Lunzat. We very carefully designed this to be able to open the black box and not rely on just trusting that the neural network had done what we think it has. And this will be what I'll be talking about in the last section. And we also very carefully made this open source, and we really invite you to go look at it and use it and break it and tell us about it, because we're very excited about talking to people. But to highlight what you can do now with this THOR methodology is to take data from an ocean model of interest. It doesn't have to be part of the CMIP framework. It could be really any ocean model, extract the input needed by the classifier, and this is the wind stress curl, the depth, and the sea surface height. They're a very commonly shared data set. We now run this through an ensemble of trained multi-layer perceptrons, and we then find the most probable class by taking the by the prediction means. And we also chose this architecture because it gave us this ability for understanding what the neural network is actually doing, which I'll be returning to. But just to demonstrate that this works here, we very carefully also completely independently validated this, where the first box shows you what we did with the original development of the neural networks, where we take these dynamics and create these labels. So what we then do to independently validate it again is that we found a model, here the CESM model, and we found one where these terms from this equation were available, and now predicted the labels, and then saw, okay, are we finding the same dynamical regime breakdowns? And the answer was yes, we are. So THOR correctly inferred this data in a completely unseen model where we could backtrack what was actually happening. And you do not have access to this data normally, even in a non-CMIP model. So we were very pleased that this was actually happening. And THOR is accurate, accessible, and explainable, and also used for climate model development, both nationally in the US and internationally in France at the IPSL lab. And I have a number of projects surrounding this that I'm very excited about. But now I want to briefly just demonstrate how THOR works and how we can do what we can do with this, also looking at the AMOC, the Atlantic Meridional Overturning Circulation. And on the right there, you can see just a cartoon of what is going on in the North Atlantic. The different colors represent the different dynamical regimes again. And what we can see is that these dynamical regimes map directly onto three-dimensional circulation. So the cartoon on the bottom there shows you in the arrows the different circulation patterns. We have the Gulf Stream on the right there by the coast. The Gulf Stream is that current that's really important, bringing warm waters up to the northern areas of Europe. And this is the one that we'll be returning to. Where what we're doing now is looking at this AMOC, this Atlantic Meridional Overturning Circulation, and we'll be looking at it in the scenario where we've abruptly changed CO2 by 4 times in the atmosphere, so really hitting the system with this hammer. And we'll be interested in what happens in what's called the new mean state. So after about 140 years, what happens? What has the system settled into? So in the modern sense, the Atlantic Meridional Overturning Circulation is what I'm showing you on the top there for one of the climate models from the Geophysical Fluid Dynamics Laboratory, the ESM model in the historical sense. So this is what it looks like now. And for this figure is a zonally mean average. So we're taking the North Atlantic circulation and we're sort of sandwiching it. And what you can see is that the red is a clockwise circulation where we have this in the surface, warm waters being brought north and then made dense to sink. And how vigorous this is, it's what's called the AMOC strength. And we know that when we increase the CO2 forcing, that this decreases. But now we want to understand why, what are the dynamics? And some dynamics of this weakening are known. But of course, how this happens in the different models is what we want to know. So we have generally known that the Gulf Stream shifts north. So here I've circled it in a little box there. We also know that how the circulation crosses the basin changes in a way where that not as much reaches north, and also that the areas where this densification happens change. But overall, we're just going to be looking at this Gulf Stream shifting here because of limited time. So what this is and how you can understand the Gulf Stream is that it initially really hugs the coast from the Florida Straits up to about Cape Hatteras on the eastern side of the United States or the western side of the Atlantic Basin. The current really hugs the coast, so it's what's called barotropic. And that means that it feels the bottom, and really the flow is very much so depth uniform. However, what happens around Cape Hatteras is that the flow lets go of the coast. So this means that the circulation doesn't feel the bottom as much, and it's really just sort of peeling away and being concentrated at the surface. So what happens here? Why does this happen? Now we can return to these dynamical regimes, and I've drawn them in a box there on the right. Like how can we understand the different regimes? And here I'm showing you this shelf area and then also going deeper. So if we have the circulation being in this light blue area, you can see it as being highly barotropic. So it cares a lot about the sea floor. But as it moves away in this orange regime, it increasingly doesn't care about the bottom so much. And in the green, it's actually peeled away even more. And in the blue, even more. And then on the pink area, it completely doesn't care about the bottom at all. So, okay, we have this understanding of the dynamical regimes. What can we do with this now, with the STOR framework? And what we can do now is what I'll be showing you. Here we have 3 different CMIT models, the GFDL ESM4 model, the UK ESM model, one from the UK, and the IPSL model from France. And here I'm showing you this historical scenario. So this is what's happening now. We've taken these surface fields and run them through Thor, and this is what we're seeing. And if you think, well, these look pretty similar, then that's right. Yeah, they look pretty similar. That's good news. But if we now apply this forcing and look at what happens after about 140 years, things start to look very different. And I know that this might be hard to see, so we're just going to be focusing in on this region around the western part of the basin. And here I'm showing you this excerpt here on the top row. And what we can see is that, yes, historically, they look pretty similar. But now if we look at this in terms of the dynamical regimes, we can see that this orange area has almost completely left the picture for all of the models. And this blue area has really changed dramatically in a lot of them. So for example, the IPSL model, things have really shifted north. And for the UK ESM model, this green area has really shifted north, but the blue area has actually widened. So this gives us a handle on what the different dynamics actually are. So this new method offers great improvement from just looking at this using one number. We can actually go in and understand more of the dynamics. And here we only looked at the Gulf Stream pattern, but there's really a lot more that can be seen. So with that, I want to jump into the last section of this talk, which I think really is one that I hope is appealing and something that you can take with you, even though you think about very different problems, because it's one that I think is incredibly important, and that's that we need to think about how we can ensure safe and transparent methods when we use these methodologies from, for example, machine learning. And here, this really doesn't need an introduction per se, but I want to emphasize that even in a climate modeling context, and certainly in a weather context, we can really bias the networks and the methodologies that we use. So if we try to just substitute something that we think is better and faster with the traditional methodologies, this can have consequences, and we really need to think about these carefully. So the grand challenge here is to develop trustworthy machine learning for science, and this is something that I discuss in a number of different publications. And on the left there, you can see just a figure of quantifying and understanding the uncertainties and the predictions in the Thor framework. And what I also want to dwell on is that I've been somewhat negative, perhaps, about how I've talked about using machine learning. But what I want to highlight here in this slide is that neural networks are fantastic. They can do things, they can find correlation patterns and make predictions that are miles ahead of what we can do with our traditional methods. And in phrasing that differently, they can solve highly underdetermined problems for us. And this means that we can learn from them. And we can learn from them also in a traditional way. But the developments we need, that I'm pushing for, is that we need to understand why predictions were made, and we need to understand how uncertain they are. So we really need to open this black box, but also understand the uncertainties involved. So here I'll be using this Thor methodology as my overall framework. But this is really applicable also widely beyond, where initially we're going to be looking at XAI relevance scores or explainable AI, looking at how we can regularize what's called the latent space, and then also develop confidence scores to have a safe and trustworthy methodology. So I said XAI, explainable AI, and this is really a family of different methodologies. And here, Thor uses one that's both neural network specific, the layer-wise relevance propagation method, but also one that's neural network agnostic, so looking at the data and the interactions of the data, or looking within the neural network. And here I'll be looking mainly at the LRP methodology, where, just as an example of what it's doing, you can look at the top left, where we've trained a neural network to recognize the image of a cat. So what we do there is that we set the different weights and biases between the different nodes. And what we can then do after we've trained the network is go backwards and add up how the different terms there really contribute. And what you can see is at the bottom left, we have this image of the cat again, and we now have a heat map showing what the neural network actually looked at. And there we can see that we have a little, we can see the little nose and the little ears. And this gives me confidence that if I present this with a new picture of a cat, it's not going to recognize the beam in the background, for example. It's actually going to look at those cat features. And that gives me confidence that I can apply this in an out of sample context, meaning present it with a completely new image of a cat. But of course, I'm not interested in cats or dogs. I'm interested in physics, and I'm interested in new physics. So the physics that might be happening under climate change that we haven't seen before. It's out of sample per definition. We do not have data from the future. So here I've shown you just substituting in the different data sets that we use for the Thor methodology. Where on the bottom you can see that we have these heat maps that are from the inputs that we've chosen. if I can remind you, we chose this input on the basis of having this rooting in geophysical fluid dynamics in this theory, in this equation. And what that means then is that I can go in and say, haha, yes, in this pink area, I know that, for example, the interactions with the bathymetry, so the seafloor, were not important. I crossed out this term using this objective machine methodology. And now going back, I've shown you these relevance scores just for these pink areas in the North Atlantic. And what we can see is that the wind stress curl term here is very important. It's very relevant. And this is exactly what I think should be happening. I know this term is important. And I can also say that here in the bottom, you can see these black lines. These show lines of bathymetry. And what you can see is that a swoop in that figure is blue, so is not relevant. And this is actually where we have an undersea mountain range, the Mid-Atlantic Ridge. So the neural network is correctly informing me that this area should not be important. And this is exactly what's the case. So I can really go in and use this Thor methodology in a completely new framework, because I know that it's actually recognizing things in a way consistent with my GFD understanding. So it's reasoning like a scientist, or like I would. But the thing that I haven't told you is that if we just do this for one multi-layer perceptron, this fails. The multi-layer perceptron does not reason like a scientist. And the way you can understand this and why this makes sense is that this problem is really, really hard. So as a cartoon here now on the left, on the right, I'm showing you just what's called the latent space, or the space that we're optimizing. And if we're training one multi-layer perceptron, on the bottom left, I'm showing you how this decision boundary might be made. I might be ending up somewhere that's a little bit off where I think I should be. So this decision boundary between the blue and the red points doesn't quite end up where it should be. But actually, if I do this again, here just adding another dot, I have another slightly better approximation. And if I keep going here, I end up with something that might be able to find this bottom. So what we've done with Thor is develop an ensemble multi-layer perceptron, or using this concept that the space that we're searching, the space that we're optimizing, is so complicated that we need to have this ensembling approach to be able to find something that's good, that's relevant. But what I also mentioned was that uncertainty is something that I think is very important. And in the Thor framework, we've now moved to using a probabilistic neural network, or a Bayesian neural network, because this allows us to have not just set values for the weights and biases, it allows us to have distributions for these. And this means that we can develop what we call confidence scores. And here on the right, I'm showing you this in terms of the entropy. And entropy in this sense can be interpreted as where you have a dark blue value, we're really sure about what's going to happen. But in the low certainty areas, there might be some ambiguity. And why is this important? Why is this exciting even? And I'll be showing you this for one area in the North Atlantic. Here, where I was showing you before, we have this transition between different regimes that can be really important. And in the red dot here, I'm showing you one area between different water masses where the neural network is really sure what's going on, but this is surprising because these should be quite different. So going in now, I'm showing you the probability of the different areas on the right, and the green bar here is showing you the correct prediction. Green is for correct, and the pink area was correctly picked out, but the blue area was very close. And this is interesting because this is this region that's just adjacent, but it's just present as a little sliver. So what's going on here? This is great, but it's also confusing. And what we can now do, and how we can learn new things even about the ocean, is that we can tap into these quantifications of what the neural network was actually looking at, and unpick what was actually going on. So here I'm showing you the wind stress curl and the sea surface height scores here with the Shapley methodologies. And you can see that for both the blue and the pink, the wind stress curl was really, really important. So this is why they're highlighted in red. But if you look at something else like the sea surface height, you can see that this was more important in the pink than in the blue. And this is really interesting because if you just look at these naively, really there doesn't seem to be much of a transition. But this then now allows me to go in and reevaluate why I thought that this was actually happening. And it allows me to think about this in a new way, guided by this neural network methodology. So it's helping me solve this highly underdetermined problem. And it's allowing me to say how it actually did this. So to wrap up here now, the goal is to develop safe and transparent algorithms for science, where I want to highlight that we need to make sure that the neural networks that we're producing are fit for purpose, especially for decision makers. And I also want to highlight that I showed you these explainability methodologies, but they are really under active development. And a lot of them actually disagree with each other. And the way that we're thinking about unpicking these neural networks is very difficult. And this is also why I usually stick with very simple ones if I can. But I think innovations within uncertainty quantification, especially within the aleatoric and the epistemic data and the model uncertainty, are very important. And of course, developing general and broad AI for climate applications is something that I think is really important and much more important than teaching neural networks or machine learning applications to search the internet for us. So with that, I want to summarize saying that we looked at what's called data mining methodologies within this equation space, and the impact this has, the impact my work has had here, is to impact US and New Zealand policy. We also looked at sparse data inference, how we can predict these key processes in models, where the impact has been climate model improvement. And we also looked at how we can ensure safe and transparent methods. And this is something that I think is really important. And I want to end with a call to action. And that is that we really need, and I'm very proud of having been part of this paradigm shift to fuse data science with domain knowledge to try to tackle some of these immense challenges facing humanity. And just finally, like Professor Pila said, I'll be moving to UC Davis. And UC Davis is really a unique place in the United States. And I'll be starting and looking for new group members. So please go to my website and look at the About section where I've put down a few words. And if this is you, get in touch. Thank you very much.
Thank you. Thank you, Maike. That was a great talk and introduction to the physics of the ocean and how to use machine learning. I really enjoyed it. And it was very inspiring. I also like to emphasize that it was great that you made it into interdisciplinary, because we could say it was very complex if you're not into the field, but you actually guided us towards understanding. So thank you very much.
My pleasure.
Let me look at the chat. If we have here, we have questions. Okay, there's no questions yet. So then I have questions. So I can take the floor now. I'm just very curious. You mentioned that one multi-layer perceptron was not enough, and you needed an ensemble. But how many? Yeah.
Go ahead.
No, just to get a grasp on how the computing performance, and also if you use Bayesian networks, perhaps it gets more complicated and you need more computing power. If you can comment on the complexity that you need to get the physics.
Certainly, yes. So for the original Thor framework, we used an ensemble of 50 multi-layer perceptrons. And there, of course, we could look at how good the prediction was and also be guided by this geophysical fluid dynamics framework. For the Bayesian approach is one that I know is a little bit controversial to some extent, and they can be very hard to train. And I think that what you mentioned in terms of the additional computational expense is one that really also needs to be taken into consideration. But the payoff for what you're able to do in this context, I think makes it very, very worth it. So being able to train something where you have access to this type of uncertainty quantification in a setting where I have demonstrated with my work that we really need this is something that I think is very, very important. So having access both to this way of looking at, okay, what's the neural network actually looking at, and how is it looking at this, is something that I would encourage everyone to think about when they're applying these neural networks. But they can be very finicky, Bayesian neural networks. So it's also an area where I'm very interested in following the developments within the machine learning community to try and learn more about what's happening and how we can think about these types of applications. Because within the machine learning community and the computer science community, the realization is growing that we can't rely on just one number. So having just one answer, the problem with a neural network is that it's always going to give you an answer. It doesn't tell you how uncertain it is. And while that's fine for a lot of applications, really for decision making or understanding the physics of the climate, that can be unfortunate and it can be misleading. And the knowledge of this is growing in the machine learning community, which means that as a physical oceanographer, this is very exciting because I can take what they're producing and apply this to my area of interest. And in that sense, both being aware of the discussions that are going on, but also being able to take them and apply them is something that, like I mentioned, and like you mentioned, having this interdisciplinary angle is just ideal for. So I'm very excited about what's happening in the machine learning community and also following it closely.
Yeah, thank you. I totally agree that the Bayesian networks and those are bringing like very important information on board. And I totally agree. We need to get used to use the uncertainty information in the applications. So it's the two things, because we're not used to having it, but if we have it, we can do really better. So I think that's a good point from the two ends, and really important for science. So yeah.
No, I completely agree. I think there are so many ways of using neural networks that for uncertainty quantification, for example, that we really haven't thought about yet. And for example, for satellite applications or generating quality assessments of data, I think there's also huge scope for really being able to tap into how these neural networks are universal function approximators. They can do things that we can't. And using that in a way that also makes sure that you're respecting their shortcomings and their limitations is something that I really think is going to be huge in the future. And when I say huge, I mean have very big, important impact.
Yeah, thank you. Totally. I have this other question about the spatial resolution of the processes, because if I understood well before, you go down the surface, but what is the spatial resolution that you need? Is it okay with 1 degree, or for getting some processes you really need to go to very high spatial resolution, or also in the vertical direction? What are the resolutions that you deal with?
That's a great question. And one of the reasons why I chose the product that I used for the initial work, this was the ECHO model. And I say model, but that's not really true, because it fits itself to available data. So it's effectively a product that's a state estimate. So it can estimate what the ocean is actually doing by tweaking its parameters to fit the data. And that means that the data fields that I have are as good of an approximation of what's actually happening as I would argue we have access to, because it uses most of the available data. So in that sense, the product that I used for developing these dynamical regimes initially, while they were from a 1 degree ocean model, they actually had the processes as they're realized in the real ocean baked in. So that's one of the reasons why I use this model. You're completely right that at 1 degree or 1/4 of a degree horizontal resolution for normal models that we use, for example, in the climate modeling context, they don't see a lot. And really the process that they don't see, like ocean eddies, these ocean weather systems, they're really important. And not having those included and not having them explicitly resolved is a big problem, because we know that they're really important, and how they're parameterized can really impact the model. So I think being able to also assess how they're represented and how they're not represented properly is something that applying, for example, the Thor methodology to, where we're developing a high resolution version now as well of Thor, is very interesting.
Okay, yeah, I understand. But I really like the way that you made the regimes classification, so you could actually divide and conquer, right? That you go to the right places and then you can just, you know, get the dynamics right and go deeper. So yeah, it was really nice. And
I like the divide and conquer. I hadn't thought of it that way.
because if you go with the whole, together, it's not. Yeah, you need to simplify. So yeah, that's okay. And then I'm very intrigued about if you have been working on El Niño under climate change. I saw it on one of your slides, because there's supposed to be an El Niño forming now next year. So the dynamics that you're studying that were not already in the predictions, like this super gyre and everything, how is that having an impact in the El Niño circulation? Or if you can comment on that.
Yeah, so the project, so the Thor framework, I just showed the North Atlantic, but the Thor framework is global. So I had a student, Zuburu Zaibu, join me initially on an internship from the Bronx Community College, but since he's moved on to Stanford, so very proud of him. And what he did was take the Thor framework and apply it to different climate models and look at the new El Niño mean state, where we could look at and track the different dynamics that may or may not be realized in appropriate ways in these climate models. So that's what he did. The project was published at the ICML in an ICML workshop spotlight paper. And what we did there is something that isn't directly related to the Southern Ocean circulation, but like, you know, it's the global climate system is global. So being able to potentially also unpick how these phenomenon like El Nino emerge, and how the different parts of the ocean and how the ocean talks to the atmosphere is related to this, is something that I think is very exciting, because I think there's a lot we don't yet know about how these big important patterns are realized, and how the ocean and the atmosphere interact to really allow this to emerge. And of course also with the land. I think the appreciation of how tied together all of these features are is really something that we're only scratching the surface of. For example, I know that there's been some attention around whether or not the forest fires that were happening, you know, had an impact on delaying the onset of an El Nino, for example. And I mean, thinking about that, and you know, is that in a climate model? Probably not yet. We should probably include that if it's one of those things that's important. So fusing different ways of looking at the system and fusing different ways of using machine learning to really unpick this emergent phenomenon that is the climate, or El Nino, is really important.
It is. And also, that was my follow-on question was related to the coupling. Have you tried into coupling the ocean with the atmosphere model and the land? I guess this is a very difficult thing, but and you went to the surface, but if you go upwards, there's the atmosphere, and then how you connect to the...
Yeah, no, that's something that I'm very excited about doing in the future. So I have some ongoing projects to start looking at this, where this coupling and finding emergent patterns in the whole system is something that I think is really, really exciting. To date, I've only looked at this from an ocean framework, where of course what I was showing you was from the climate model. So the climate models are coupled, so they take the different components of the climate and realize them, you know, with an ocean model and an atmosphere model on top, and, you know, a land model next to the ocean, and these all talk to each other. But actually discovering these dynamical regimes, or these parsimonious equations-based representations, is something that I think has a lot of scope for insight that could really help us understand the climate system. Of course, taking a modeling framework and then porting it to observations and going back and forth, because of course the model is not the real world, but understanding the real world without the model is very hard. So there's this feedback between the different frameworks that I think is really exciting and actually underutilized. I think the different communities, even within disciplines, really need to talk to each other more.
Yeah. And then I have this one other curiosity, and then we go to the chat. It's you saw this map in which there was the Antarctica in the center, and then the Earth around. That was a very nice perspective. You know, we are really used to see the Antarctica in the UTM, and then I want to know if you have investigated the implications of this supergiant. So because it understood well, it was not in the models as an important dynamic, and then now that was a scientific breakthrough. So how does it impact what we know, or do you have any grasp of that, or that's ongoing?
That's something that I'm actively thinking about, yes. So the implications there are very many, and this is a work that I was very excited to lead. The implication from a modeling framework is that the way that we think about how we realize the interactions with bathymetry are very important. So for example, if you have something that kind of looks okay, then you really need to make sure that circulation emerges from the right physics. And I've revealed that the interactions with bathymetry there, these undersea mountain ranges, is really important. And there, the thing to note is that normally this is studied in what's called idealized models, and they might not even have bathymetry. They might just have little ridges that might not even be zonal. They might just have, you know, the Antarctic Peninsula sort of sticking out a little bit. And the insight we get from that is not something that we can apply necessarily to these really complicated models. So we need to think about that. And that was one of the insights. Well, we need to think about many things, but I think that one's important. The other
this is really new. So.
The other thing I want to highlight is that one of the authors on that paper was an observational oceanographer, Chrissy Reeve, wonderful scientist. And the exciting thing about having her on that paper is that while this was, you know, with the ECHO model, so tied to observations, but not actual observations, what she was able to add was this appreciation of, okay, this is how we use observations. This is how we collect observations right now. What are the implications for what could we be missing if we were to observe somewhere else, guided by these dynamical regimes, which, like I demonstrated, we can predict. You know, how does this matter? How do we interpret and reinterpret the observations that we already have? So in that sense, that's also one of the things that I'm really excited about going forwards in the future, and hopefully collaborating with more observational oceanographers.
Okay, we have questions on the chat from D. Silverman. Its first question is, how does your perceptron approach to ocean climate inform or integrate with ecosystems modeling?
That's a great question. So some of my work has also looked at plankton ecosystems and finding emergent ecological niches within those. And this is not something that we've directly applied yet, but the implications here for ecosystem modeling is that the ecosystem and the carbon cycle and so many other things are really tightly coupled to the ocean circulation. So for example, in the Southern Ocean that we were just talking about, how warm waters are being brought up is not just important for the ice. It's also important because those water masses have a lot of nutrients in them. So these different materials that the plankton, for example, the microscopic plants and animals at the base of the food chain, what they eat. So in that sense, by having an appreciation of what the physics are doing, we can also tie this to understand different variations in the ecosystem that might be happening.
Okay, interesting. It gets more complex, but
it is very complicated. That's what makes it interesting.
Is it? Okay, second question is about any thoughts on modeling organismic physiology fluid flows? It's somehow connected to the previous.
Oh, that's fun. I have many thoughts, of course, but I think the one that might be most relevant here is that if you mentioned modeling, and modeling there, I think applying methodologies to understand the different potential regimes within a model is something that can really help us understand the different ways the different components of the model interact, and thus also have scientific breakthroughs. So I'm the dynamical regime methodology that I presented, or this way of thinking about, okay, I have this really complicated set of equations. What do I do with them? How do I understand this? This is a very old problem. So if you go back to what's called the hydrodynamic paradox, this was something that ground fluid dynamics to a halt for, I think, 150 years, until Prandtl came along and said, hey, there's this boundary layer. And this was something that he was able to discover, but really the breakthrough that was in fluid dynamics, to just understand that there was this tiny layer that he was able to observe, that then allowed them to unlock this beautiful field where they'd had this problem of reconciling different areas. You know, that's something that with machine learning we can do, because recognizing that there are certain things that co-vary, and when I say co-vary, I mean that different terms really come together and are important in a statistically significant way. That's something that as humans, it's really hard to see. But in an objective sense, machine learning methodologies can help us do that. So in terms of modeling organismic physiology and fluid flows, this is something that we might not have as verifiable equations around, and now I'm referring to my knowledge of the ecosystem models that we use for climate models. But I'm sure there is scope for making fundamental progress by applying similar techniques.
Nice. And then I think we can get this third question. We're out of time, but that's okay. What are next level challenges and limits, in particular with using the perceptron as a basis for modeling?
Oh my goodness, that is a very big question, especially to end on. The next level challenges, I think the ones that I would encourage the community to really look at and care about are the last section of my talk. So this concept of creating safe methodologies, safe, transparent methodologies, because I think the scope for both making sure that what we design is fit for purpose, but also the scope for learning and for guiding and really creating breakthroughs is huge. So what we need there, like I mentioned, is knowing why the neural networks or the perceptrons made their decisions and how uncertain those decisions are. And once we unlock those two, I think really the sky's the limit in terms of, if we have the data, we can understand what covariances are in there using machine learning, and then help us guide our discovery and also our development of these really important new techniques.
Yeah, thank you. If I can add, I'll say that the new technologies and new data sets, as you as you mentioned, are key, and new tools to exploit them are also very fundamental. So I see that's next level challenge to be able to exploit all of this. That's a golden age for scientific
Very
breakthroughs.
exciting time to be a scientist.
Yeah. Okay, so I'd like to thank you, Micah, again for staying with us today. This is now time in the neural network if you want to join and ask other questions there. And thank you all for attending. Thank you. Yeah.
Thank you for your attention.
Yeah. Bye.
Thank you for participating in today's AI for Good session. We hope you've learned something new, innovative, and engaging in today's event. We now encourage you to continue the conversation on the live video wall in the neural network. Here you can ask questions, like and comment, share links, complete the poll, connect with interesting profiles, or speak one-on-one using the chat and video function. We invite you to explore the lobby, try the smart matching quiz, visit the virtual exhibits, poster boards, the eShop, and build your personalized AI for Good program. Let's shape the future of AI for Good.
AI is a powerful tool.
This summit can help ensure that artificial intelligence charts a course that benefits humanity and bolsters our shared values.